In this episode, we're going to take regression output, which often looks like a confusing wall of numbers, and turn it into a set of ideas you can read like a story. Beginners tend to assume regression is only for people who love math, but regression is really about explaining and predicting a numerical outcome using one or more input variables. The exam is not trying to see whether you can derive formulas, but whether you can interpret what a regression model is saying and spot when that story is weak, misleading, or incomplete. Regression output includes pieces like coefficients, residuals, significance indicators, and fit measures, and each piece answers a different question. If you mix them up, the output feels random. If you separate their roles, the output becomes readable. The goal is to help you build that separation, so when you see regression results in a question, you can quickly identify what matters, what it implies, and what common mistakes to avoid. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start with the idea that a regression model is a structured relationship between inputs and an output, not a magical truth detector. The model assumes that the output can be described as a baseline plus contributions from each input, along with error that captures what the model does not explain. That error is not a shameful leftover. It is an honest acknowledgement that real-world data is messy, incomplete, and influenced by factors you may not have measured. When you fit a regression model, you are choosing coefficients that make the model's predictions as close as possible to the observed outputs, according to a chosen fitting rule. The model's job is to produce useful predictions and interpretable relationships, but its success depends on how well its assumptions match reality. Beginners often treat regression output as a definitive answer, but it is more accurate to treat it as a summary of how well the model describes the data under the modeling choices made. The exam often tests whether you can interpret with this cautious mindset rather than making absolute claims. Coefficients are usually the first thing people look at, and they are the easiest part to misread if you do not understand what they represent. A coefficient describes how the model expects the output to change when one input variable increases, holding the other variables constant. That holding constant phrase is essential because in real datasets, inputs are often related to each other, and the coefficient is trying to isolate one variable's relationship with the output while controlling for the others. If the coefficient is positive, the model associates higher values of that input with higher predicted output, all else equal. If the coefficient is negative, the model associates higher input with lower predicted output, all else equal. Beginners often think a coefficient is just a correlation, but it is a conditional relationship inside the model, not a simple pairwise association. Exam questions might ask you to interpret a coefficient in words, and the safest answer describes direction and unit-based change while keeping the all else equal idea in mind. The intercept is another coefficient, but it has a special role that can confuse beginners. The intercept represents the model's predicted output when all input variables are zero, assuming zero is meaningful for those variables. Sometimes that makes sense, like a baseline cost when usage is zero, and sometimes it does not, like a predicted score when age and experience are zero in a dataset where those values never occur. The intercept is still useful mathematically because it anchors the prediction equation, but its real-world interpretation depends on whether the 0 point is within the scope of the data. Beginners sometimes overinterpret the intercept as a deep fact, when it may simply be a baseline needed for the line to fit the data. On the exam, if you are asked what the intercept means, explain it as the predicted outcome at zero inputs. But be cautious about claiming it is meaningful if the scenario suggests zeros are unrealistic. This kind of cautious interpretation is often what distinguishes a correct exam answer from a tempting distractor. Now we move to residuals, which are where you learn whether the model is doing a good job or just producing impressive-looking coefficients. A residual is the difference between what you observed and what the model predicted for that observation. If the model predicts perfectly, residuals would all be zero, but real models rarely do that. Residuals are valuable because they show patterns of error, and patterns of error often reveal what the model is missing. For example, If residuals tend to be positive for high input values and negative for low input values, that suggests the model is systematically underpredicting in one region and overpredicting in another. If residuals grow and spread as the predicted value increases, that suggests the variability of errors changes across the range, which can violate assumptions and affect interpretation. Beginners sometimes treat residuals as boring leftovers, but residuals are often the key to diagnosing problems like nonlinearity, missing variables, or outliers. Exam questions may not show plots, but they can describe residual behavior and ask what it implies, so it helps to understand residuals as evidence about model fit. Significance in regression output is another area where beginners get tripped up because it looks like a stamp of truth when it is really a conditional statement under assumptions. When regression output reports a p-value for a coefficient, it is typically testing a null hypothesis that the true coefficient is 0, meaning the input has no linear relationship with the output in the model's context. A small p-value suggests the observed relationship is unlikely to be due to random sampling variation alone, given the model assumptions, while a large p-value suggests the data does not provide strong evidence that the coefficient differs from 0. The key is that significance is not importance, and it is not causation. A coefficient can be statistically significant but practically tiny, especially with large datasets. A coefficient can also be practically important but not statistically significant if the dataset is small or noisy. Exam answers that treat significance as proof of causation or as proof that a variable matters in the real world are usually wrong, because they overclaim what the test supports. A related concept is the standard error of a coefficient, which reflects uncertainty in the coefficient estimate. If a coefficient has a small standard error relative to its magnitude, the estimate is more precise. If the standard error is large, the estimate is uncertain, and that uncertainty often leads to a larger p-value. Standard errors are influenced by sample size, variability, and how much the input variables overlap in information. If two input variables are highly related, it can be hard for the model to separate their effects, which can inflate standard errors and make coefficients appear less significant even when the model predicts well. Beginners sometimes think a model is broken when a variable becomes non-significant in a multivariable model, but that can happen simply because another variable already explains the same signal. On the exam, this shows up as questions about why a coefficient's significance changes when adding another predictor. The right reasoning often involves shared information and uncertainty, not a magical disappearance of relationships. Fit is the big picture question. How well does the model describe the data overall? And how useful are its predictions? Regression output often includes measures of fit that summarize how close predictions are to observations on average. One common idea is that the model explains some portion of the variability in the outcome, while the rest is left in residuals. Another idea is that fit should be considered relative to purpose, because a model can have a decent fit for prediction but still have misleading coefficients for interpretation if assumptions are violated. Beginners sometimes want a single fit number to decide whether the model is good, but fit is multidimensional. A model can fit well on training data and fit poorly on new data, which is overfitting, and regression output alone may not reveal that without additional evaluation. The exam often asks you to interpret fit cautiously, recognizing that a fit measure describes performance on the data used for fitting unless stated otherwise. You want to think of fit as evidence, not a guarantee. A common interpretation trap is confusing goodness of fit with correctness of individual coefficients. A model might produce a high overall fit, while some coefficients are unstable or misleading due to correlated predictors, outliers, or misspecified relationships. Conversely, a model might have a modest fit, but still reveal a meaningful relationship for one variable that remains consistent across different samples. The right way to read regression output is to keep the roles separate. Coefficients describe the model's learned relationships, residuals describe what the model got wrong, significance describes uncertainty under assumptions, and fit describes overall performance. If you blur these roles, you might incorrectly argue that a significant coefficient proves the model fits well, or that a good fit proves every coefficient is meaningful. Exam questions often include these logic errors as distractors because they sound confident. Your defense is the role separation you are building right now. With that separation, You can explain what each output component means without claiming it answers questions it was never designed to answer. Another important concept is that regression makes assumptions about the relationship between inputs and output, and when those assumptions are not met, interpretation becomes risky. A basic regression model assumes a linear relationship between predictors and the outcome in the way it represents them, and it often assumes errors behave in a stable, random way. If the true relationship is curved or has interactions, a simple linear model can produce patterns and residuals that signal misspecification. If there are extreme outliers, they can pull coefficients in misleading directions because the model tries to reduce error overall and may sacrifice many normal points to accommodate a few extreme ones. If the dataset includes variables that were influenced by the outcome, you can get leakage-like situations where coefficients look strong but do not reflect real predictive causality. For exam purposes, you do not need to fix these issues, but you should recognize the symptoms and avoid overconfident interpretations. If a scenario describes strange residual patterns or unstable coefficients, it is often hinting that the model form is not capturing the true structure. You should also understand that regression outputs are context-sensitive, meaning that changing the data can change the story. If you train the model on a different population, coefficients can shift because relationships differ across contexts. If you change the scale of an input variable, the coefficient changes because it reflects change per unit, even though the underlying relationship might be the same. Beginners sometimes panic when coefficients change after rescaling, but that is normal because units matter. This is why interpretation should include units and direction rather than focusing on raw coefficient magnitudes without context. It is also why comparing coefficients across different models can be tricky if variables are not scaled consistently or if the models include different sets of predictors. Exam questions might test whether you understand that coefficients are not universal constants. They are learned relationships conditioned on data, model choice, and variable definitions. To read regression output quickly on an exam, you can adopt a mental order of operations that keeps you from getting distracted by the wrong details. First, identify the outcome variable and what the model is trying to predict or explain, because everything else depends on that. Second, interpret the sign of key coefficients in plain language, including the all else equal meaning. Third, look at uncertainty indicators like standard errors and p-values for those coefficients, but interpret them as evidence, not as proof. Fourth, think about residuals as the model's misses and whether the scenario suggests systematic error patterns. Fifth, consider overall fit as a summary of how well predictions match observations, while remembering that fit on one dataset is not the same as generalization. This mental routine is fast because it mirrors the structure of the output itself. It also helps you avoid spending too long on one number while missing the bigger story the question is testing. To bring it all together, regression outputs become readable when you treat them as a set of coordinated answers to different questions rather than as a single verdict. Coefficients describe how the model expects the outcome to change with each input, while keeping other inputs constant, and their signs and units matter. Residuals describe what the model failed to capture and can reveal patterns that signal missing structure, outliers, or violations of assumptions. Significance and standard errors describe uncertainty in coefficient estimates under a testing framework, but they do not prove causation or practical importance. Fit measures summarize overall prediction performance on the data at hand, but they do not guarantee future performance, and they do not automatically validate every coefficient. If you can keep these ideas separated and then connect them into a coherent narrative, you will be able to answer regression interpretation questions with confidence and avoid the classic traps that rely on overclaiming. That is exactly the skill the CompTIA Data AI exam wants to see. Not advanced math, but clear reasoning about what model outputs mean, what they do not mean, and what you should be cautious about.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.